Now, I think you realized that last time when I said that the camera was not working, indeed it's almost okay. I mean, we just missed the last 10 minutes, so I think it was not a big problem. Now, I just wanted to have a look at the schedule to see, at the calendar to see where we are. So, today is April 15, and then we jump to 2 weeks from now. Sorry for that, but there is the Easter break, as you know, which is not bad. And also it's, the Easter break doesn't allow us to teach on Thursday next week because it's April 25, which is a public holiday in Italy. Okay, that's it. And let's jump to our topic today. And I go back to the page of deductive methods for water resources assessment. We concluded the treatment of IMOD, and we had also the experience with the computer regarding the application. I'm sure that probably you would like to discuss the code some more, but next time when we meet in May, we will have another session on the PC, and I suggest to postpone the discussion of the code next time when we have the PC. And then I wanted to speak a little bit about groundwater. A little bit because it's groundwater modeling is treated in other courses in civil engineering in our degree program, and it's also a subject that is quite extended. In fact, there are other courses that are focusing on it. However, groundwater modeling is extremely important also for water resources management and water resource systems in general, and therefore I wanted just to give you an overview of how the equations that are used for surface water modeling can be adapted and applied in order also to model groundwater resources, because the equations are just the same. We discussed in rainfall runoff modeling, we discussed the mass conservation and conservation of momentum energy. In groundwater modeling, we use the same equations. It's again a movement of a fluid. It's in the domain of fluid mechanics, and therefore the equations that we used are precisely mass balance equation and the conservation of momentum, which translate under simplifying conditions in conservation of energy. So same equations. So what's the difference? The difference is the domain. In the domain and the fact that the processes are observed in a different way. Meaning that when we talk about surface water, it's something that we can see. I'm not saying that it's easy to monitor, because monitoring of water resources, even when we talk about surface water, again, it's a bit complicated, but it's something that at least we can see. When we talk about groundwater bodies, they can be seen only by identifying the location where they emerge, sources of fresh water, and can be observed, the groundwater bodies, through wells or through holes that we dig in the soil in order to check what is the level of groundwater. But observation is more difficult. It's not so immediate. And the identification of the control volume, which means the spatial domain where we apply conservation of mass and conservation of momentum, it's a bit more complicated, because when we talk about surface water, we have an ideal reference, which we assume as a control volume, that is the catchment. Sometimes the catchment is difficult to identify, because we already talked that we already discussed that sometimes when we take the divide, the topographic divide has boundary of the catchment, we make errors, because it may happen that the divide of groundwater into a catchment, precisely because we cannot see it, is different from the topographic divide. But nevertheless, it's clear that when talking about surface water, the catchment is an ideal reference for identifying the control volume. You may say that the catchment is a surface and not a volume. In fact, when we apply surface water modeling, we include also the groundwater part. But in surface water modeling, we usually assume that it doesn't play a significant role. This is true when we talk about flood flows. It's less true when we talk about low flows, and this is the reason why we try now to focus a little bit more on groundwater. But when we talk about groundwater, as I said, the identification of the control volume is more difficult, and the definition of the geometry of this volume is more difficult, and also the definition of the hydraulic properties, because it's clear that the movement of water in a porous media is also regulated by porosity, by the lithology, by the type of soil, which are things, properties that cannot be easily observed. So this is the difference. This is why groundwater modeling is more complicated. But there are some behaviors of groundwater that allow us to simplify the problem. And as we will see, the most distinguishing behavior, which allows us to make a substantial simplification of the problem, is that flow underground is very slow. And this makes things easier, because it's clear that when we have to model something that is rapidly changing, it's much more difficult than modeling something that changes very slowly. In fact, when we talk about groundwater models, usually we refer to ample, large time scales. So we don't talk about daily groundwater level, hourly groundwater level. We usually talk about monthly groundwater levels or seasonal groundwater levels. And we are allowed to do that because the changes are very slow. And this, as we will see, is a great simplification. Because, as I said, to model short-term variability is much more complicated. Okay, so let's see, when we talk about groundwater models, how we treat the problem. I don't have slides for this, but the reason is that, as you will see, my treatment is very, very brief. And I just scroll down the web page, and, oh, sorry, because, okay, I need to magnify these equations, because these are included in the web page as images. I will magnify it, okay? So, let's then place the basis for deriving the groundwater flow equation. Like in surface flow, we have equations that are driving our models. For groundwater, when we combine conservation of mass and conservation of momentum, we derive an equation which we call the groundwater flow equation, which is the combination, as I said, of conservation of mass and conservation of momentum. We combine these two equations into just one. And of course, there are unknowns. There are unknowns that we will need to compute by integrating the equation. So again, what we express is an equation with partial derivatives. The groundwater flow equation includes, as we will see, partial derivatives. The reason why we need to refer to derivatives is that we need, again, to refer to volumes that are quite small, because there is heterogeneity. And then, in order to identify the variable, we need to integrate these equations into a larger domain. Okay? So, the groundwater equation starts from two assumptions which are listed here. Fluid is incompressible. This is fine. I mean, when we talk about groundwater, we don't have, the movement of water, as I said, is very slow. We don't have to deal with very high pressures, usually. And it's very difficult, very rare the case in which the groundwater body is so deep in the underground that we have to take into account compressibility of water. So usually we make this assumption that fluid is incompressible, and also we assume, but this second assumption can be easily removed, that there are no sources of water mass in the control volume. This can be easily removed. Meaning that if you have a source of mass inside the control volume, you just have to add it to the conservation of mass equation. So it's not a big problem. But let's start from these two assumptions, and let us denote with the following symbols, the following variable. So W, which depends on the three spatial coordinates, and time is the storage in the control volume. Storage in control volume. Okay, and we indicate with Q in, again depending on the three spatial variables and time, and Q out again depending on the three spatial variable and the time. These are inflow and outflow through, I'm writing, through the boundaries, through the boundary surface of the control volume. The boundary surface. Okay, these are our symbols. And now we can write the continuity equation. Let me magnify it. Sorry, I think I need to mirror the screens just 1 second, otherwise in this way it's very difficult. Okay. Just give me 1 minute. I need to mirror the screen otherwise. Okay. My relationship with this projector is dramatic. Okay. Good. Okay. This is the conservation of mass equation. I'm writing it here. Okay, so given these symbols, storage in the control volume and in and outflow, after the control volume has been identified, we can write very simply, as we did for the linear reservoir, we can write that the partial derivative of W, which depends on the three spatial coordinates and time with respect to time, is equal to Q in minus Q out. So this is very simple. Okay. And this is what you can find written here. Now, we have to find an expression for Q in and Q out. And in order to do that, let's refer to a sketch of a control volume, which is here. Okay, let's assume that this is our control volume. And it's a control volume in the 3D space, of course. So we have a flow that is entering the control volume through the three faces of this cube. And then we have a flow that is exiting Q out through the opposite faces of this cube. So, for instance, in this case, we have a flow that is entering, which is Qx, and Q, what is Q? Q is the flow per unit area through the direction x. And therefore, in order to compute the total flow Q in, we have to multiply lowercase q times the dimensions. If this is Qx, we have to multiply it by the z and the y. Okay, so we can say that Q in is equal to Qx lowercase q, which depends again on the three spatial coordinate and time, times the z, the y, plus, here we have qy, which depends again on the four coordinates, times the x, the z, plus qz, again x, y, z time, x, the y. So this is our Q in. And then you can imagine that in the next step I'll have to substitute Q in the equation above. But before that, let me write Q out. So if we refer to this Q, we have Qx entering it through here, and then exiting in the x direction through, as I said, the opposite phase. But what is the value of the flow per unit area? What is the value of lowercase qx in the opposite phase? It's not the same value, because we moved for a step the x along the x direction. So there is a variability, because we see that qx depends on x. So there is a variability along this phase, which we have to take into account. And therefore, Q out will be written as Qx x, y, z tau plus partial derivative of Qx x, y, z tau with respect to x in the x. And this is the flow per unit area that goes out, which needs to be multiplied in order to obtain the total flow times the z, the z, the y. And this is in the x direction. And then we have to write the outflow for the other two directions, which I'm not writing here. You have to bear with me, because I don't have room in the blackboard, but it's clear. But then I have to go with qy, which will become qy plus partial derivative of qy with respect to y, and multiplied times the y. Everything is multiplied for y in the x, the z. And then there is the third term. Everything is clear? Okay. It's clear also that when I go to substitute in the above equation, conservation of mass, there are terms that cancel each other, because I will have Q in, which is given by this along the x direction, minus Q out. And if I go again to the x direction, I find the same term here, which is subtracted. So these two terms compensate each other when I go to substitute up there. And what remains is only this partial derivative. So now I can go and substitute, given that I have a small blackboard. I can write here, I need to delete here, Q in minus Q out. This is equivalent to, when I take Q in given by this equation and Q out given by this equation, what remains is minus, I go here, partial derivative of Qx, x, y, z, t, with respect to x, in the x, the z, the y, minus the partial derivative along y, minus the partial derivative along z. And this is what we obtain. It's shown in the web page. I go above a little bit. So if you look here, you have the partial derivative with respect to time of the volume stored, which is given by the left-hand side of the equation there. And if you go down to the last row, you see that there is precisely written what I have written on the blackboard, but there is also here mentioned, they are reported also, the inflows and outflows in the y and z direction. So this is where we are on the blackboard we got here. Everything is clear? Okay, the groundwater flow equation is another topic that is not very, it's very easy indeed, but in the notation that becomes a little bit complicated, because also when you write variables by keeping explicitly highlighted the dependence on the 4 coordinates, the equations become complicated, also complicated to remember. So try to see the concept behind, which is very easy. It's just change over time of a storage, which is given by in minus out, and in minus out is given by the partial derivative of the flow along the three directions, which are multiplied by the dimension of the control volume, which is really, it's very simple, the concept, but the notation, I recognize that it's a bit difficult, and when the notation is difficult, everything becomes more complicated, especially for an engineer, because we are not used to see the concept behind the mathematics. We are used to look at the concept, and then connecting the concept with the mathematics is something that it's not so easy for us. Okay, now, of course, here it cannot be solved because we have several, here we have several unknowns. So W is for sure an unknown, but also other unknowns are in and out. We don't know these variables, Qx, Qy, and Qz. We don't know them. So the equations, this equation alone doesn't allow us to solve the problem, which is also something that we can easily understand because it's just a mass balance equation. We didn't consider conservation of momentum so far, conservation of energy. So at this stage we have to introduce here something related to the conservation of momentum and energy. So let's move forward and let me get to, let's move forward in this way. I'm trying to center because this is an essential step. We now define a variable which we call capital S subscript S, SS, has the volumetric specific storage, which is simply called very often specific storage. What is that? It's the volume of water that an aquifer releases from storage per unit volume and per unit decline in hydraulic head. So let's try to clarify the concept. We have a control volume, and we have inside this volume water with an energy content which is summarized by the hydraulic head. What is the hydraulic head? In an unconfined aquifer, the hydraulic head is the energy of the fluid particle, which is summarized by what is called head, which is the water level. It's just potential energy. Why only potential energy? Because the kinetic energy can be neglected because the movement is very slow. So usually when dealing with groundwater, we assume that the energy content of the body is given by the water level. The water level can be a free surface in the groundwater if the aquifer is unconfined. We discussed the difference between a confined and an unconfined aquifer. So if the aquifer is unconfined, the head energy content is given by the groundwater level. So if we have a well, we look into the well, we see the water level into the well, and this is the head. If the aquifer is confined, the head is given again by the water level, which is, in this case, higher than the roof of the aquifer. So even in this case, what we can do is to dig a well and see to what level water comes up higher than the aquifer, and we can see what is the level that water reaches. Sometimes it may be higher than the ground level, which means that we have to, with a pipe, we have to check what is the level that is reached by groundwater. But keep in mind that when we talk about groundwater head, hydraulic head in groundwater, this is the water level in all the cases, which can be the level of free surface or can be the level that water reaches into a well. Okay. So, if the head is the energy, if we change the head, we have a release of water from groundwater. We have a movement of water. If we have a change in the head in an aquifer, we have a movement of water, which can be also understood if you think that the head is something like the water level. So if you change the water level, for sure you have a movement of water. You have water that is displaced. So it's reasonable to say that, it's completely justified to say that if I have a change of head, then I have a release or an accumulation of water. And therefore, we introduce this quantity, this volumetric specific storage, which is given by, per unit change of hydraulic head, is given by the release. Release can be negative or positive, of water from the groundwater body per unit volume of aquifer. So this volumetric specific storage has a dimension of 1 over length. Okay, if we identify this volumetric specific storage, we can rewrite our mass balance equation simply in this form. Again, the change of volume with respect to time is given by the volumetric specific storage times the unit volume, because remember that storage is water released per unit volume times the change in time of the head. So the specific storage multiplied by a volume multiplied by a change of the head is precisely a volume. And given that the change of the head is given in time, what I obtain at the right-hand side of the equation is precisely a change of volume in time. So it can be rewritten in this way. But by rewriting the equation in this way, I'm now considering something that is related to change of energy. So this is an equation that introduces conservation of energy. The past version was an equation that just accounted for mass balance. This is an equation that is now taking into account conservation of energy, because it expresses the change in volume depending on a change in energy. So it's clear that there is a energy equation in there, which we will have to express clearly. SS now is just a definition. We will have to provide an analytical expression for SS, which will be an energy balance equation. So what I'm writing here, it's a different equation with respect to what I have derived here. We express the same variable, change of storage in time, depending on a different right-hand side. Because this is an energy equation and this is a mass balance equation, but it's clear that we now can combine them. We can say that this right-hand side part of the equation, we can equate it to the right-hand side of the mass balance equation. This is what we want to do. In fact, I'm sorry, every time I have to scroll back. In fact, if I now pass to this equation, what you see is that the two right-hand sides are now equated. So I am combining the two equations that I derived so far. I'm sorry, I could rewrite it on the blackboard, but it's very long and I cannot fit in this blackboard, so give me just the permission to write the simpler forms later on the blackboard, okay? I understand that looking at the screen is not the best. It's not the best for you. Now I'm cleaning the blackboard to get ready for the next steps. So let's look at this equation now. We have on the right-hand side, we have these flows or changes of flow through the three directions. And on the left-hand side, on the right-hand side, we have the change in storage given by the multiplication of change in head times the volumetric specific storage. It's clear that in order to move forward now, I have to give an expression for this SS. I have to basically introduce an energy balance equation which is more defined. Keep into account that the flow, when it's expressed along three directions, like in this case, it can be interpreted as a vector. So the flow here has three components along the three directions. It can be interpreted as a vector. We are used in surface water to consider the flow as a scalar because we work in one dimension. And therefore, in surface flow, you may remember, we didn't go into the details, but you may remember from fluid mechanics that we assume that the flow is 1D, because we usually deal with a river, and the river, we can assume that the flow is 1D. And therefore, we are used to treat the flow, which is volume of water per unit time, as a scalar. But actually, when the flow is 3D, in three directions, you can assume the flow has three components, and you can assume that it's given by a vector. This is just a premise that I make because as you will see later, we will treat indeed implicitly the flow as a vector. Implicitly because we are still talking about the flow in three directions here, so it's not identified as a vector, but explicitly, but indeed we could do that. Okay, so this is where we are. Let's move forward. Okay, now this equation can be written in a compact form. And the compact form, so let me just show you. We were at this stage. First of all, we see that we can divide the left and right hand side by the x, the y, the z, okay? And therefore, if we do that, we get this form which is more compact. It's simpler. And therefore, we can use the operator nabla to write the left hand side. And we obtain this. The operator lambda is the divergence. So this is why I introduced the premise that the flow can be treated as a vector. Here now we have at the left hand side the divergence of the flow, which is equated to the release per unit volume from the aquifer, the release of water per unit volume through the aquifer. Okay. Now, as I said, this equation, which I just shown, I forgot to say that. Let me show it to you once again. This equation has two unknowns, Q and H, flow and head. So clearly cannot be resolved by itself. Okay, we have to introduce additional